load test, pull-out test discussion on slides number 11, which I explained before your winter break, in which we have some limitations in the pull-out test, which are that at the interface between the plate and the cylinder, there might be friction. Due to reaction at the interface between the concrete block and the plate, there will be compression in this concrete. So as a whole, the cylinder will be under compression. And as a matter of fact, cylinder means that concrete is in compression and only steel bar is in tension. So friction at the interface will restrain the lateral expansion or dilation. The compression will restrict opening up of the cracks. So in reality, when you have a bar in beam, bar is in tension and the concrete surrounding the bar is also in tension. So that is the reality in beams elements. However, in this test setup, we have the different environment surrounding the bar. So bar is enjoying a good strength of concrete around it because concrete is in compression and tension crack can't open or widen in the compression domain. So that is one demerit of this pull-out test, that based on this pull-out test, the development length, which I will calculate, that may not be true representation of the actual conditions in practical structures where bar is in tension and the surrounding concrete is also in tension. So that is the reason, in addition to pull-out test, it is recommended to carry out beam test also. In that beam test, what will be the condition that you will be deflecting the beam by putting some UDL or point load, and as a result, when bar will be in tension below neutral axis, the concrete will also be in tension, and then whatever relationships you will develop, that will be close to actual conditions. So based on beam test, then the relationships will be more reliable, and not alone based on pull-out test, you can develop trustworthy relations. So this was a brief introduction about the average bond stress, true bond stress, and some test setups I explained, like prism test or beam under 1 point or 2 point loadings, and then finally the test setup of pull-out test. Now on this slide number 12, we want to discuss mechanism of bond transfer. Very simple explanation is given here. A smooth bar embedded in concrete develops bond by adhesion between the concrete and bar and by a small amount of friction. So only two mechanisms are present. One is natural chemical adhesion between steel and concrete, and second is small amount of friction at the interface between steel and concrete. Both of these effects are quickly lost when bar is loaded in tension, because when you load the bar in tension, it will elongate, it will reduce in area, its dia will reduce due to stretching of the bar, and because the diameter of the bar decreases slightly, and that decrease is understandable, we are well familiar with the Poisson's ratio of which is the ratio between lateral strain over axial strain, and steel has the Poisson's ratio, that effect. So as a result, when bar dia will decrease slightly, debonding between the smooth bar and the concrete will take place, and hence in that case smooth bar will be easily slipped out. In cases where smooth bars must be embedded in concrete, so there is no other option except to provide smooth bar as reinforcement, then it is always recommended to go with some mechanical anchorage like hooks or bends, or maybe some headed reinforcement, or plates may be welded at the end to develop the anchorage against slip. Because in smooth bar only mechanism is friction and chemical adhesion. Although adhesion and friction are present when a deformed bar is loaded for the first time, now we are talking about a deformed bar which is now practiced in reinforced concrete. So it is mentioned that adhesion and friction, which are the mechanisms against smooth bar, are also present in case of deformed bar. And when a deformed bar is loaded for the first time, these bond transfer mechanisms are quickly lost, leaving the bond to be transferred by bearing on the deformations of the bar. So in contrast, in smooth bars there is no deformation, so there is no bearing component. While in case of deformed bars, on slide number 14, we can see this picture where we have shown schematically the deformations on the bar surface. So when tension is applied, and against that tension the reaction is offered, and that reaction is actually offered due to bearing on the deformed bar, and deformations on the bar are causing this bearing component, and the reaction is inclined, because in this picture the lugs or deformations are slightly inclined, and normal to the surface the reaction or bearing component is taking place. I can resolve this bearing component into two components: along the bar and then normal to the bar. And this is actually the reaction which is offered, and in this way on the picture C, components of the force on concrete are shown, and they are resolved that what bar is being subjecting to concrete is actually the component which is normal to the bar, and we call it a radial component, and a component which is along the bar we call it longitudinal component. Actually this was the action, and the reactions are shown, reactive components are shown in picture C. So we can understand that the component which is along the bar will be offering friction or resistance against slip, and the component which is normal to the bar will generate pressure on the concrete which is surrounding the bar. So on the B part of the picture we can also see the schematically what I am talking about, that we will have one component normal to it, other component which is along the bar, and this component which is normal to the bar length, tangential, it is generating internal pressure, and this pressure is also shown in this picture, which is D part of the picture, radial forces on concrete, which, and if that pressure will exceed the concrete tensile stress, then there are chances that splitting up of the concrete cover will take place, because concrete surrounding the bar will act like a cylinder subjected to internal pressure. So these hoop stresses are actually being generated in the shell concrete, and once the stresses exceed the tensile strength of concrete, splitting of the concrete may take place. So it is mentioned here that on slide number 13 that equal and opposite bearing stresses act on the concrete as shown schematically on slide number 14. The forces on the concrete have both longitudinal and radial component. The latter, which is the radial component, causes circumferential tensile stresses in the concrete around the bar. Eventually, the concrete will split parallel to the bar, and the resulting crack will propagate out to the surface of beam, and these cracks are called splitting cracks, and the splitting cracks follow the reinforcing bars along the bottom or side surfaces of the beams. So we will talk about the splitting cracks classification on next slide. So actually, who is responsible for the splitting cracks? The radial component, and that radial component is causing actually the circumferential tensile stresses, and as a result, once these tensile stresses will exceed the tensile strength of concrete, splitting will take place. And while reading these paragraphs, we understand that the cover concrete is very important, and its quality is also important because it is subjected to internal pressure due to the deformations on the bar surface, and once you apply more and more force on the bar, and once bar is approaching yield strength, more and more internal pressure will be generated. When bar is at low stress, obviously the radial component will not be huge, but if you will apply more and more force and it is approaching yielding, more internal pressure will also be generated. So as a result, as we said, that splitting will take place. On this slide number 15, let me change the tab. Now my slide number 15 is visible to you?
Yes, sir.
Right. Now on this picture, slide number 15, I want to show you typical splitting failure surfaces. Now first is, we call it side cover. In some textbooks you will call it side split failure mechanism. So actually the failure mechanisms are because of the splitting failures, and the tangential component is actually causing the internal pressure, and as a result cracking may approach the surface of the beam. So in this picture A, it is important that if your bar has insufficient edge cover, we learned that ACI recommends us that the bar edge cover should be not less than uh, the clear cover should not be less than 1.5 inch or 40 millimeter. Then we learned that there will be a tie of dia 10 to 13 millimeter that will envelop the longitudinal steel, and then the center of the bar will come, and that bar may be number 25 or number 19. So in this way we have some distance from center of the bar to the edge of the beam, and in this distance from edge to the center there is some space occupied by the clear cover, then the tie dia, and then half of the dia of the bar. Now if the edge cover is insufficient, and furthermore if both the bars are closely spaced, we learned in the PRC1 that code recommends that the clear gap between the bars should be greater of the least diameter of the bar, 25 millimeter, and third was 1.3 times the coarsest aggregate size. If for example we have number 19 millimeter, the coarsest size of the particle, then we will end up with about 25 millimeter if the dia of the bar is also 25. So more or less we may have, if bar dia is 25, the recommended clear gap between the bars again around 25 millimeter. Now imagine that while placing the steel in the formwork, you compromised on the edge cover, and you also compromised on the clear gap between the bars. So what then will happen when you will apply more force and at the maximum stressed section when bar will approach yielding? As a result, the tangential component will cause more and more internal pressure, and those pressure circles may merge because of the insufficient gap, and those pressure circles may touch the edge of the beam, and the instant your hoop stresses will exceed the tensile strength of concrete, a splitting crack will develop, and along the beam length you may find that there is a crack running at the level of the steel bar. That crack on the edge, on the sides of the beam will be visible. However, the crack which is in between the bars may not be visible because it is concealed. But the instant these cracks will merge and they will propagate and they touch the edges, chances of the complete spalling up of the cover may take place. So in this way, the complete debonding of the bar along the beam at highly stressed regions is quite possible. So this is also shown on this picture, picture A on slide number 16, that on the top picture there are cracks which we call them structural cracks. We are well familiar with the web shear cracks where shear is dominant. We are well familiar with the flexural cracks where bending tensile stresses are dominating. We are well familiar with the flexural shear cracks where both flexure and shear will merge. And we are familiar with the hogging domain where tension is on top and again flexural cracks are present. And near the support we are familiar with the web shear cracks. So all these are structural cracks. In addition to them, if we have some bond failures, splitting failures, we may also find that there are cracks which are also running on the beam surface, and at the edges they are getting visible and they are running along the length of the bars, and they are more prominent at those positions where splitting failures are taking place. So this you can see that crack is running and finally it is merging in the flexural shear crack. In this picture A, because of the insufficient soffit cover, pressure circle touches the soffit and the crack actually touched the soffit of the beam, and then you may find at the soffit of the beam a longitudinal crack is running, and finally it is touching the flexural crack. So such cracks which are visible at the level of the steel layers are the signs of splitting failure in the beam. So it is stated here that when you have a sufficient bottom cover, then it is possible that these circles are not consuming the tensile strength of concrete at the soffit, and splitting is not taking place at the soffit, but on the sides and in between the bars cracks are propagating. While in picture B, we have another situation that edge cover is insufficient and soffit cover is also insufficient, but the gap between the bars is reasonable, so the pressure circles are not merging and the tensile strength of concrete is not approaching. So as a result, the crack propagation at the level of steel layer between the bar is not obvious, but there is a crack which will be visible at the soffit running along the bar and on the sides. So in such beam, you may get that along the beam length, bars are visible on the sides and at the soffit as well. So this also shows that there are insufficient bottom and edge covers. There is a third situation that although the side cover was reasonable, so the tensile strength is not approaching, between the bar gaps are sufficient, so the splitting is not taking place, but the soffit cover was so inferior and the splitting is not only taking place at just one point, which is just below the bar, but there are more radiating out cracks which are touching the soffit of the beam, and rather is one line crack propagating at the soffit along the length of the bar, multiple cracks get visible at the soffit, and chances are that a V notch, a V-shaped chunk of the concrete may be spalled off, and in some textbooks this type of failure is called V-notch failure mechanism. And the first picture is called side split failure mechanism. The second picture in some books you will call bottom split failure mechanism. Actually bottom and side both are splitting. And third one is called V-notch failure mechanism. All these are actually typical splitting failures due to either insufficient edge, bottom, or the clear gaps between the bars. Now there is a fourth possibility that if the cover and the bar spacings are large compared to bar diameter, so this is another scenario that there is no problem with respect to the bottom cover, side cover, and pressure is not touching any of the edge or the bottom, but still the possibility is that bar as a whole is sheared off, it is pulled out. So rather than getting multiple cracks on the surface, suddenly the bar is slipped out. So if the cover and the bar spacings are large compared to the bar diameter, a pull-out failure can occur where the bar and the annulus of concrete which has good bonding with the bar surface, and that annulus of concrete is between successive deformations of deformed bar. So it means that concrete which is actually sandwiched between the deformations, so that piece of concrete. So what will happen when bar will be pulled out, the hole which will be generated in the concrete surface as a result of slip of the bar will be bigger than the die of the bar. It will not be plainly slipped. Along with that, it will also shear off the annulus of concrete, and between successive deformations pull out along a cylindrical failure surface, joining the tips of the deformations will be actually sheared off. So this pull out failure is more critical because without warning, suddenly this kind of slip may take place, and it is possible that even before yielding, you were anticipating that beam is tension controlled, under reinforced. Beam will give us lot of warning. It will give us 0.005 and bigger strain in steel before crushing of the concrete. But sadly, we got a sudden slip or a sudden pull out because of the insufficient grip of the bar due to improper development length calculation. So as a result, we may get a brittle failure, and we may state that a bond failure occurred well before the predicted tension controlled under reinforced failure. Now we learned that based on pull out test, that we have the opportunity that on that simple pull out test, if I am putting the bar in the jaws of the machine, I'm gripping the bar in the jaws of the machine and I'm applying load on that bar, I can note down that at what load this bar is pulled out and the needle stopped, and then I can use my simple equilibrium equation to calculate either the bond stress, or against a certain load I can calculate that what length I require to hold that force. So let me go back to our basic equation first. Simple equation from which we started our discussion. This one, for example, if I have in mind what is the force I want to apply on the steel, because the left hand side is actually delta T, Fs2 minus Fs1 into area of the bar will give me actually a delta T, because stress into area is that force, change in force. And in addition, if I have the information about the average bond stress between the steel and concrete, I have the information about the die of the bar. Against a delta T, knowing the average bond stress, I can calculate what length I need to resist that force. If I consider that this delta T will be based on actually Fy. For example, I say Fs2 is actually Fy and Fs1 is 0 into pi dB square over 4 will give me actually what delta T? It will be delta Ty. It will be that force which I can calculate easily by multiplying the area of the bar with its yield strength. For example, if I have number 25 bar and that number 25 bar is of steel grade 420, what force I can maximum generate in that bar will be 420. What is it? The grade into the area of the bar, nominal area 510. So in this way, I can calculate a force which is Ty, and that is the maximum force. If bar has on one tail, on one end, the zero stress, and on the other face, on the other section, the maximum stress Fy. So what will be then delta Fs? Delta Fs will be actually delta Fy into pi dB square over 4 will give me actually Ty. Furthermore, to introduce factor of safety, I can multiply this with 1.25 or 1.3 to any factor which I want to further incorporate as factor of safety in my applied force. It may be 1.2, 1.3. Let's increase it to 20%. And then if I know the average bond stress based on my test results, experiments, whether pull-out test or beam test, provides me that for this concrete grade, what maximum average bond stress I can develop. With this simple equation, I can calculate the length which I then need to develop the equilibrium between the exaggerated force, which is 1.25 times delta Ty or Ty, and I can bring mu average pi dB as denominator on the left hand side to get that length. That length, I will call it a development length. The length which is required.
Hello, hello. Yeah,
सर का मैं नेट पे चला गया लाइट
हाँ, मैं यही कंफर्म कर रहा था।
नहीं सर लीव कर गए हैं
चलो बस छुट्टी हो गई है।
जी अस्सलाम वालेकुम।